So our next talk is efficient Gaussian process inference for short-scale spatio-temporal modeling, and our speaker is Jaakko Luttinen.
Okay, thank you. Hello, I'm Jaakko, and the topic is Gaussian processes for spatio-temporal modeling, and this is joint work with Alexander Ilin. So to begin with the problem setting, so we have an unknown spatio-temporal field which is a function of location and time, and we would like to learn this field from a set of noisy observations. And now the requirement for the input set is that we have a set of locations and a set of time instances which don't need to be evenly spaced or anything, but at each time instance we get observations from that set of locations. So the input set is a Cartesian product of the locations and the time instances. We can have missing values, but this is like the baseline. So in order to model the functions, we use Gaussian processes which make it possible to set distributions over the functions, and they are characterized by a mean function and a covariance function, and you can draw samples from it also. And the problem with Gaussian processes is that the computations scale cubically with respect to the number of data points, and there are roughly two different approaches. Maybe you can, if the function is a long scale function, you can use, for example, low rank approximations of the covariance matrix. If the function is a short scale, you can use, for example, compactly supported covariance functions, so the covariance matrix will be sparse, and you can utilize sparse matrix algorithms to gain some speed. And so we're now interested in these short scale phenomena. And so the covariance matrices that follow, you can assume that they are sparse. So we begin with a very simple model where the covariance function is separable. Means that the overall covariance is a product of a covariance over the spatial domain and a covariance over the temporal domain. And given that the input set was a Cartesian product, this results in a covariance matrix which is a Kronecker product. And this Kronecker product has nice properties. For example, if we don't compute the full covariance matrix explicitly, the memory requirements are reduced significantly because we can just store two small matrices, the temporal covariance matrix and the spatial covariance matrix. And we can do some operations like a Cholesky decomposition. We can do it separately in the temporal domain and the spatial domain, and then just combine the results. And the same applies to inverting the matrix, just inverting both domains separately. So it's very efficient to deal with these much smaller matrices than the full matrix. And also matrix vector multiplication is also very efficient. But now I would like to construct a bit more complex covariance. So this is the Kronecker product covariance matrix that we had before. And now first we add some noise to model some realistic observations, and then also we might have missing values, so we need to remove those rows and columns from the covariance matrix which correspond to the missing values, and this can be done with a matrix operation where this I tilde is an identity matrix where you remove the rows corresponding to the missing values. And then if you want to model different length scales or something, then you can have a set of these covariance matrices and by having a sum. And again, if we don't compute explicitly the covariance matrix, then the memory requirement is reduced significantly, and so we can just like store the building blocks. But now the Koleski decomposition and inversion, we cannot do them efficiently. It would require computing the full covariance matrix, and we don't want to do that. But still, fortunately, this matrix vector operation is very efficient because the covariance matrix was built as matrix operations. We can just apply the matrix operations sequentially to the vector, so those operations are efficient. So how to do inference with the model that we introduced? So one of the standard ways would be to integrate out the function values and then learn the hyperparameters by drawing samples from the marginal posterior or maybe optimizing it. And well, that's the density function. And then how to learn the function values, can, for example, compute the mean and the variances of the function values, maybe the diagonal elements of that covariance matrix. That would be the standard approach, usually. But now that the Koleski decomposition is computationally too expensive, we cannot compute the log determinant of the covariance matrix. And then, but the function values, we could compute the mean by using some iterative methods to solve the matrix vector system. But to compute the variances, it would be too expensive to solve that matrix system. So we propose to use skip sampling instead. So draw samples from the conditional posterior distributions in terms the function values and the hyperparameters. And now the question is how to draw samples from these conditional distributions efficiently. And then in skip sampling you might have strong coupling between the parameters of the variables, and in order to the skip sampler to work well, you need to reduce that coupling somehow. So these are the questions that now need to be solved. And for the function values, we can do this kind of sampling. We first draw samples from the prior, and then we transform the samples from the prior, and actually that is a sample from the posterior. So in a bit more detail, we first draw samples from the generative process, the function values and the data, and then we use that transformation given the data and then given these f tilde and y tilde samples from the prior. And if you compute the mean and the covariance of that transformation, see that it has the correct moments. So this in general applies to Gaussian distributions. You can draw samples from the posterior like this. If these two steps are efficient to do, then it's a good way. And now in our case, this generative process, sampling from the prior, that's very efficient because the prior covariance matrices have Kronecker product structure. So it's easy to generate the data. And the transformation is also efficient. It's just need to solve matrix vector system, and you can use conjugate gradient method for that, for example. Then how about sampling the hyperparameters? Well, the conditional density function is cheap to compute. There's no problem with that, but the main problem is that these hyperparameters and function values are strongly coupled. In Gaussian processes, there's a strong structure in the prior. So if you have a lot of function values given, then the distribution of the hyperparameters is almost like a delta distribution. So we need to reduce that coupling somehow, and we'll do a change of variables. So we want to make this transformed z as independent of theta as possible by this linear transformation. And ideally, this would whiten the posterior distribution, in which case Z and theta would be independent and the Gibbs sampler would be very efficient. But of course we cannot compute the posterior covariance matrix, so we cannot whiten the posterior. But because in Gaussian processes there's a lot of structure already in the prior, maybe if we whiten the prior distribution already helps enough. So, and the prior distributions are again easy to compute, and we can whiten the prior distributions. So let's see how well this works. Now here's a comparison between the standard using like the marginal posterior and the Koleski decomposition approach, and then using this Gibbs sampler. So the red line is the standard approach and the blue line is the Gibbs sampler. And because there's a high autocorrelation between the samples, especially in the Gibbs sampler case, we compute the effective number of samples and we show the CPU time for one effectively independent sample. So in the x-axis is the number of data points, and then y-axis is how much time it required. So by comparing the solid lines, the amount of time for the effectively independent samples, this Gibbs sampler was approximately maybe 100 times faster. And the memory requirements also limited the size of the data sets. So this marginal posterior could be used only for something like maybe 50,000 data points, whereas this Gibbs sampler could be used for 10 million observations in this setup. So then a real-world experiment. So we had global sea surface temperature data. We have 1,700 locations over the globe, 1,600 time instances, but we have approximately half of the data is missing. Especially in the early years, the amount of missing data is significant. And so in total we have 1.3 million observations, which is quite a lot for Gaussian process regression. And the goal is now to reconstruct the missing values. But of course we don't have the missing values because they are missing, so we need to use test sets. And we use two kinds of test sets. The first case is such that we pick data points randomly with probability 0.2. The problem with this approach is that the test points tend to be very close to other observations. So using this short scale method, it might be too easy to reconstruct. And so we try to make the setup a bit more realistic. We use the pattern of missing data from the early years, where we have lots of missing data. We use that pattern. And in the recent years, we have lots of data. So we use that missing value pattern to remove data from the recent years. So we have the same missing value pattern than we have in the real case. So that should somehow simulate the real problem. And we compare to principal component analysis and then to Gaussian process factor analysis, which is basically just PCA, but you put Gaussian process priors over the factors. So for the uniform case, we had two short-scale Gaussian processes. The first one used only one covariance function, like one length scale. The other one was a sum of two covariance functions, modeling two different length scales. So for the uniform test set, these short-scale GPs had smaller reconstruction errors, but there was no difference between these two short-scale GPs. For the, interestingly, for this pattern case, pattern test set, these short-scale GPs also performed tests, and there you can even see that adding another covariance function so that you're able to model two different length scales then improves the results. And okay, so that's it. Summarized. So I presented a spatial-temporal Gaussian process model for short-scale modeling, had a non-separable covariance function, and presented a Bayesian inference method which draws samples of the hyperparameters and the function values, and it was applicable to very large spatial-temporal data sets. Okay, that's it. Thank you.
Okay, we've got some questions.
What was the data source for the C-surface data?
I think it's MOHSST, MOHSST. I'm not sure about, I don't remember. It's in the paper at least. Sorry.
Yeah, so I didn't quite understand the motivation at the beginning for considering short-scale kernels for the GP. Could you just go over that again?
Why we model short scale?
Yeah.
Okay, well, so for this long scale phenomena there are these, you can use inducing inputs approach, for example, or then this Gaussian process factor analysis. They are good for modeling the long scale or global phenomena, but they usually aren't sufficient, so you might want to model also the short scale. So now this is the short scale. You might want to combine it with the long scale model, so you're able to model both long scale and short scale phenomena. But yeah.
So it seems like, at least based on the graphic you're showing there, it seems like almost basically no smoothness, like almost no smoothness going on in the short scale case. Is that what you're...
Sorry, I didn't get it.
So it seems like almost no smoothing is occurring in the short scale case. Like the GP is just sort of drawing lines between successive data points.
Yeah, okay, true. That's not a very good.
Just sort of a feature of that graph and not the general case.
Yeah, it's more feature of this. They might be more noisy. Yeah, if I put more noise, then maybe you wouldn't see anything. So, but yeah, at least in this sea surface temperature data, they are very noisy. So you can see the smoothing. Yeah.
So your regression, the experiments show that the GP mean is really good, but do you have an idea of how well the variance is?
I'm thinking whether I computed some measures for that. I don't have a definite answer for that now, but yeah, I think it's a good question too. You should really see the distribution, not just the mean. Yeah. Yeah.
Any other questions? Okay, let's thank the speaker.